All right, welcome everyone to lesson 24, where we're going to introduce the concept of a triple integral. And don't worry, it's not as scary as it sounds. It's a little bit scary, but it's not as scary as it sounds. But before we go into triple integrals, let's take a step back and think about single integrals. This Saturday, there's going to be Integration Bee hosted by the math department. And an Integration Bee is kind of like a spelling bee where the person who's best at integrating, in this case, is going to be the winner. So the way it's going to work is there's going to be like an elimination round where you have like a sheet of several integrals to do, and then the however many people who score highest on that will go to the bracket elimination round where you have to do integrals faster than other people. So it's kind of a fun competition. It's going to be over Zoom. It's going to be this Saturday at 12 p.m. So if you feel like you want to test your integration skills, go ahead and head to that. It's going to be all Calc 2 stuff. It's not going to be any multiple integration or anything like that. So anyways, that's on this Saturday. There might be prizes. I'm not sure. I forgot in the email if there are prizes or not. There might be. I don't know. I don't want to hype it up if there aren't, but you know, when I did this in undergrad, there were. So anyways, let's go ahead and get started here. So triple integrals, what are these going to be? Well, with double integrals, we integrated with our domain being both the x and y plane, or sorry, yeah, the xy plane, because we have two variables. So now if we want to integrate a function of 3 variables, then our domain needs to have 3 variables as well, x, y, and z. So what we're doing is, so back in Riemann sums, we broke up our domain into a bunch of little intervals, right? X1, X2, X3, X4, and we found rectangles for these heights. So this is Calc 1 with a single integral.
Yes,
All right. What was that? Oh, okay. Yeah, be sure you're muted if you're not saying anything. Okay. So then next we have double integrals. So here we split up the one-dimensional domain into pieces. With double integrals, we looked at our domain in the xy plane, and we broke those up into squares. And then we have a 2D domain for double integrals. So we have these tiny little squares, delta x and delta y here. So naturally, with triple integrals, what we're going to be doing is we're going to have our 3-dimensional domain broken up into these tiny little cubes. So let's imagine we have this tiny little cube here with a very thin width, length, and height. And what we're going to do is we're going to pick somewhere in this cube to evaluate our 3-variable function. So maybe, I don't know, maybe we'll just pick the middle of the cube, kind of like how we could pick the midpoints here, the middle of this square for single and double integrals. So we'll pick the middle of this cube. We'll call that point xi, yj, zk, depending on which square this is, and we will plug it into a function. So we plug the middle of this cube into a function. Okay, there we go. And the value of this times dv is going to be our value for this little cube. And what we do is we keep doing this over all of the little cubes in our domain until we've gone over the entire domain right here. All right, so then what is the triple integral? Well, kind of like how we had a single sum, a single Riemann sum for single integrals. We had 2 sums, 2 Riemann sums for our double integrals. We're actually going to have 3 sums for our triple integrals here. So yj, zk times delta v, and this is the volume of this is delta v. So we're adding this up over all of the possible x values. So I going from 1 to say n. We're adding this up over all the possible y values, j going to m. And then we have k equals 1 to l for all the z values. And what we're doing is we're sending m, n, and l to infinity. So these cubes are getting tinier and tinier and tinier but we're having more and more of them until finally, as our limit goes to infinity, we have our triple integral here. Now, the nice thing about these two back here is that they had nice geometric interpretations. The geometric interpretation for our original integral was area under a curve. And then what's the geometric interpretation for a double integral over some region? What was the interpretation for that? Yeah, it was going to be a volume under a surface, right? So then if we apply that same reasoning here, what's the geometric interpretation for a triple integral? It would be hypervolume, or maybe space-time if you're doing physics, underneath a hypersurface. And that's getting really abstract. That's not a very useful way of thinking about this anymore. So triple integrals get kind of difficult because we lose our sense of kind of physical grounding, like we lose our geometric sense with these right here. So it's a bit more difficult to think about triple integrals geometrically, but we could still evaluate them in much the same way that we did with double integrals. So that actually kind of begs the question, what do we actually do with triple integrals? I imagine not a lot of people are computing hypervolume of things, although maybe some are. Anytime you have something that has the word density attached to it, like maybe charge density in electricity and magnetism, or probability density in statistics, or maybe mass density if you're doing mechanics, any of those are going to have a triple integral involved. So those do show up relatively often, so that is an application of triple integrals. And Daniel actually has a good question. Can we find volume like we did area with double integrals? Yes. So we're going to talk about that later. If we do the triple integral of 1 dV, that will give us the volume of the region that we're going over. So we could also use triple integrals to compute volumes as well. So they're not totally abstract or like totally useless or anything. There still are reasons why we want to compute a triple integral. All right, so let's go ahead and try one. So let's start with the basics here. Kind of like how we started off with the basics for double integrals, where we just integrated over a rectangle. We're going to start off easy with triple integrals, and we're just going to integrate over a cube or a rectangular prism here. So, or a box. You guys could just call it a box. So B is going to be our box. These are the range of X values, of Y values, of Z values right here. And how do we integrate over the box? Well, we just take turns doing the integral of each variable right here. And we just go ahead and do the integral with respect to each variable, plug the numbers in, and then move on to the next one here. Okay, so let's do the triple integral of x plus yz squared dv, where b, the thing we're integrating over, is this box here. So why don't we do this in alphabetical order here, although we could really do it in any order according to this. We have dx, dy, and dz right here. So x goes from -1 to 5, y goes from 2 to 4, and z goes from 0 to 1. So let's go ahead and do this here. So let's do the x integral of all of this. So the x integral of x is x squared over 2. The x integral of yz squared is xyz squared. This goes from -1 to 5. And then we still have our other bounds here. All right, let's go ahead and plug this in. Let's see, so we have 25 halves here. We have 5yz squared here. And then we subtract -1 squared over 2, so it's -1/2. And then we subtract a negative here of yz squared, so that's plus yz squared. All right, and if we simplify this, this part will become 6yz squared, and this part will be 24 over 2, aka 12. All right, let's go ahead and integrate here. So we're going to integrate with respect to y. So 12's integral is 12y. The integral of 6yz squared will be 3y squared z squared. We do this from 2 to 4 right here. So I'm going to go ahead and plug in 4 for my y. So I plug 4 into here, I'm 48. I plug 4 into here, and I have y squared, which is 16, and then times 3 is another 48. Then I subtract 2 times 12, and I subtract 2 squared times 3z squared. So that's minus 12z squared here. Yeah, that's okay. All right. And finally, we just have one more integral here. Oh, is it 3 or 6? No, it's 3 because this was 6yz squared. We raised the power to 2 and then divided by 2 right there. All right, so let's combine this to make our life a little easier for the next integral. This is 24, and this is 36z squared. So integrating this with respect to z, we've finally gone through all of the integrals. We have 24z plus 12z cubed. This goes from 0 to 1. So I plug 1 in for both of these here. I have 24 plus 12. 0 will yield 0 for that. And we end up with 36 for this triple integral right here. Is it possible to change the order of integration in 6 different ways because there are 3 variables? Yes, we will be seeing that in a minute. So with double integrals, there are 2 ways of doing it. You got to do the x first or you do the y first. With this, there's 6 different ways of ordering 3 things. So there's going to be 6 different ways of doing each integral. Now, just like before with double integrals, some ways are certainly better than others, but that's a little bit ahead in the future. All right. So that's doing a triple integral over something simple like a box. So what happens if the 3-dimensional region we're integrating over is not just a box? What if it's something that looks a little bit more complicated? Well, there are 3 types of solid regions that we can do triple integrals over. The first one is where z is in between 2 different surfaces here. And this is called type 1, where z is a function of x and y, and it's in between 2 of those. And then what happens, so the way this works is we do the z integral here. We do the z integral. And then once we do the z integral, then we end up smushing everything down in that direction. So once we do the z integral, once we take care of that first iteration of the integral, we sort of crush everything down to its shadow, which in this case would be d right here. That's how we're going to think about doing these triple integrals. So algebraically, what does that look like? Well, first we'll do the z integral of our function. We're going to do the z integral of our function, and our lower bound for this is u1, and our upper bound is u2. So we're integrating from this bottom surface all the way to this top surface. Those are the bounds here. All right, so we do that with respect to z, and then once we do that, we sort of crush everything down and get rid of the z, and we just focus on x and y's here, and then we do a double integral over the remaining x and y's. And this could be either dx dy or dy dx, whichever way is easier to do it. Or maybe you could turn it into polar coordinates or something like that here. All right, so this is how triple integrals work. We do the z integral first maybe, and then we just revert everything down to a double integral, which we now know how to do those. That was type 1. What are type 2 and type 3? The only difference between type 2 and type 3 and type 1 here is which variable we're doing first. And to be entirely honest with you, I don't remember which one was which with this. So I guess we're just going to call type 2, we're going to have y is u of x, z. So we would do the y integral first, and then we're going to crush the y dimension and then do a double integral with x and z. Or we could have x as a function of y and z. So we would do the x integral first between 2 surfaces in the x direction. We would crush that down and then do a double integral in the y and z dimensions right here. All right. Isn't this just the second lesson from this unit, but in 3 variables? Essentially, yeah, it is. So we're adding this extra step where we do this integral between two 2D surfaces, and then we end up doing a double integral, which has a 1-dimensional bounds here, and then 0-dimensional points as our last bounds. All right, this is a bit abstract. Let's go ahead and try to set up a real triple integral here. Okay. Okay, so write an iterated integral for the triple integral over the region E of f of x, y, z, dv. So they don't tell us what function this is, so we can't actually do the integral, but we could at least set it up. Where E is the region in the first octant, bounded by the surface 9 minus x squared minus y squared and the coordinate planes. All right, let's go ahead and do that. Let's see here. Where do they want us to go? This one. Okay. All right. So let's draw this first. And with triple integrals, you still want to draw your region here. So z is 9 minus x squared minus y squared. This is an upside down paraboloid. So it's going to start here at 9 and then be a parabola going down like that. And then we have a parabola going down like this. And then connecting them at z equals 0 is a circle right here. So this is our surface right here. And remember, it's in the first octant. So these are walls right here. And then this is a wall down here. All right. So let's go ahead and set up this triple integral. So we're bound with this function. Let's say we wanted to do dz first. So let's do dz first. And that's usually my default bound to do first is dz. But that's not the only way to do these, of course, but that's usually the way I try to start doing them. Okay, so what's my lower bound? So what's my 2-dimensional surface lower bound here? What's the lowest surface that we hit with z? What's the name of this surface down here? It's z equals 0. That's right. We're bounded below by the xy plane, which is a 2-dimensional surface. So this is z equals 0. Okay, so that's our lower surface. Then what's our upper surface? What's higher in the z dimension? Remember, it's got to be a surface here. Yeah, it's going to be 9 minus x squared minus y squared. What would happen if we just used 9? If we just use 9, that would be the plane z equals 9, and this would be a box rather than this curved figure right here. So that's the difference between z equals 9 and z equals this paraboloid here. Okay, so we finished doing the z dimension, right? So what we need to do now is we need to crush down the z dimension. So we're going to crush this down, and we're only going to focus on what we have with x and y, which is this right here. So we don't care about z anymore. We've already done z. We're focusing on what's going on in the xy plane here. So we look at this projection here. So what is this? Well, if z is equal to 0, if we crush that down with z equals 0, we have 0 is 9 minus x squared minus y squared. Or in other words, x squared plus y squared is equal to 9. So this is going to be a circle of radius 3 right here. All right, so if this is x and this is y, why don't we do y next? Although we could have done x, that wouldn't have been a problem. So now that we're looking at this picture, this is like the top-down view where we've gotten rid of z right here. What would be our lower bound 1-dimensional curve? What would be our lower bound curve for y? What is this? This is y equals 0. That's right. That's a constant line here. Okay. And then what's our upper curve here? What's our upper curve for y? What's the equation of this with y? Square root of 9 minus x squared. Absolutely right. So if we solve this for y, we have root 9 minus x squared, and we pick the positive one because we're in the first octant here. So this is the square root of 9 minus x squared. All right, and then once we have y done, then we crush down the y dimension, and then we only have x. So our last integral will always just be two numbers or 2 points. So if we crush down everything right here, we have our lowest point with x and our highest point with x. Our lowest point with x is 0, and our highest point with x is 3. So this would be the integral right here. This would be how we would compute this triple integral over this particular region right here. All right, so I want to emphasize here how we think about this. We have an upper and lower surface. Then for the next integral, we have an upper and lower curve. And then for the last integral, we just have upper and lower points or numbers. And that's always how it goes. And if we just have a double integral, we ignore the 2D part, and we're going to have 1D here and then 0D here. So we go up a dimension each integral deeper. It's more like we go down a dimension. So we have 2 dimensions, then we're focusing on a 1-dimensional boundaries here, and then 0-dimensional boundaries right here. So that we're kind of taking a step down in dimension for every integral we do. Okay, now as someone mentioned earlier, there are many different ways that you can order these integrals. And by many, I mean 6, because there are 6 different ways of ordering dz, dy, and dx here. And just as it was with double integrals, there are going to be some ways of ordering them that are going to be much more convenient or even possible to do than others right here. All right. I'm going to set up all the work and then forget a negative sign. Yeah, that's the bad thing about multiple choice exams. But we'll try to make something, we'll try to kind of split this up so you don't, so that's less likely to happen. Would that integral that we did give the volume? If this were 1 right here, it would give the volume. But as it stands right now, we don't know what function this is. This would give the hypervolume over this region under this hypersurface. But again, we're not going to think about it in that way. That's not really productive here. So don't think about this physically right here. All right. So what we're going to do in this next exercise, and I really want you guys to pay close attention to this next exercise. This is probably the most useful exercise you can have for setting up triple integrals. So you really got to pay attention to this part. So focus on this right now. All right, what we're going to do here is we're going to express this integral in 6 different ways, where E is the solid bounded by the surfaces y squared plus z squared is 9, which is a cylinder, x equals -2, which is a plane, and x equals 2, which is another plane right here. Okay, so now there are three different variables we can start with, right? I'm going to do the integrals that start with dz first. I'm going to do dz first. Okay. Now let's see here. How about we do dz, dy, dx? We'll reverse alphabetical order here. Okay. So we need to see what our upper function is with respect to z. So what's our upper function here? What is this kind of curved thing right here in terms of z? Z equals what? That's right. It's going to be the square root of 9 minus y squared. And it's okay that there's not an x in there. The x not being there just represents that we can have any x value. So my upper bound here will be root 9 minus y squared. And then what's my lower bound? What's this down here going to be? That's right. We're going to have the negative version of it because we just have the circle on the bottom here. Okay, great. So those are going to be my bounds there. And actually, we can start work on our second one already, since the next one will be dz, dx, dy. We do z first, so these are going to be the same bounds for the starting integral. Okay, now here is where we need to use our imagination here. We're going to crush down this cylinder flat. So we're crushing down the z dimension. We don't have that anymore. If we crush this down flat, what shape will we get in the xy plane? We're going to get a rectangle. Very good, very good. So we're going to get a rectangle here. Now, our lowest x value that we have was -2. Our highest x value was 2. All right, and then our lowest y value, what's our lowest y value that we have? Yeah, it's going to be -3, right? And then our uppermost y value will be 3. So if we squash this cylinder down in the z dimension, so we get rid of the z dimension here, then we're going to end up with this rectangle right here. So make sure you guys see that. Pay close attention to this picture and try to see that here. We're crushing down the z dimension and we end up with this rectangle here. Okay, so now let's go back to this integral. So we're doing our one-dimensional lines here, right? So what's our lower bound that's a one-dimensional line for y? It's just -3 right here. And then what's our upper bound? Our one-dimensional line for that, it's going to be 3. And remember, I emphasize these aren't just constants or numbers. These are actual functions. So this is y equals -3 as a line and y equals 3 as a line, even though those are just numbers right here. How do we know when to use double versus triple integrals for finding volume? We'll talk about that in a little bit. All right, and then finally with x, so now we crush down the y dimension and we just only have the x-axis now. Now our lowest point on the x-axis is -2 and our highest point on the x-axis is 2. So that'd be how we would finish off this integral right here. Now let's go to the next one here. Here's where we did dz first, so we already saw how that worked. And then now we have dx and dy. So we crush down the z-axis, we get this same picture, right? Only this time our one-dimensional things will be in x now. So we have this one-dimensional curve and this one-dimensional curve. So our lower one-dimensional curve, lower in terms of x, will be -2. And our higher function of x will just be 2. Then we crush everything in the x direction, and we only have the y-axis left. And when we only have the y-axis left, our lowest point is -3, and our highest point is 3. So this second part was actually pretty easy. We ended up just kind of flipping the order there. And that makes sense because remember, when we have only numbers as bounds for our integrals, we can just flip the order of the integral. That was one of the first things we talked about with double integrals here. So you could do the multiplication trick. You could do the multiplication trick once you get down to this level. So you need to do the z integral first, and then you could do the multiplication trick when you do the y and then the x. Why I do dz dx dy rather than dz dy dx? We're doing all 6. So we're trying to see what all 6 versions of the integral here. All right, what's the multiplication trick? It's where you have constant bounds here, and then you could just split up your integrals to integral with respect to x times an integral with respect to y, and you can kind of split them up. Could we use symmetry? We don't know what this function is, so we don't know if it's symmetric at all with respect to this cylinder here. If we were finding the volume of this, then we could use symmetry. Or better yet, we could just use the volume of a cylinder formula. That'd be way better than doing this. All right, so now we have 4 more integrals to do. How about we do dy next? Okay, so we're going to have dy, and then maybe we'll have dz dx. And then we'll have dy, and then we have dx dz. Okay, now remember our guiding equations here are y² plus z² is 9, x is -2, and x is 2. So now we're doing things in the y dimension first. So how can I get y as a function of all of the other variables, or at least one of the other variables? How do I get my 2-dimensional surface for y? Same as z, but you use z instead of y. That's right. Yeah, Ryan's got, yeah, we got a bunch of people got it right here. That's right. So if we look in the y direction, our furthest surface in the y direction is this, right? And this is going to be the square root of 9 minus z squared. And that's for both of these. So we're looking at the circle in the y direction. All right. And then obviously, if we go the other way, we're going to have the other version of the circle right here. So we're going to have negative root 9 minus z squared throughout the function. Okay. All right. Now what we're going to do after we've done the y integral is we crush out the y dimension because we've already done that. If we crush this in the y direction, so we crush it this way now, what shape are we going to have? It's going to be a rectangle again. That's right. So it's going to be a rectangle, but this time the rectangle is going to be with respect to x and z. So we're crushing this down this way, and now we're focusing on the xz plane. So we already know what our lowest and highest x values are. We have -2 and 2. And then what will our higher and lower z bounds be? Yeah, it's just going to be 3 and -3 like before. And when you think about it, this kind of makes sense geometrically because here we kind of just crushed it down on the top, and here we're crushing it down on the side. We're still pushing on the circular part of the cylinder, so we're going to make the same shape. It's just going to be rotated differently. So we get a rectangle with this too. Although some people I already see in the chat are suspecting something different might be true for the next set of them, and you're right. What happens if you crush it, doesn't make a nice uniform shape? We'll see about that with the next one here, because that's going to happen. All right. So let's see here. So our upper bound with z is 3. Our lower bound is -3. And then and remember, these are lines. So we're talking about the line z is 3 and the line z is -3. And then we have our 0-dimensional points from -2 to 2 for x. And here we just flip it. We look at this in the other way. So we have our higher x line here, our lower x line here. So -2 to 2. And then we crush it in the x dimension. And then we have z going from -3 to 3. All right, so it's very much the same as before right here. All right, now the next part's going to be a little bit different. So for the next part, we're going to go and do this with respect to x. So we have dx, dy, dz. And then finally, we have dx, dz, dy. Okay. Now let's go back up here and look at this picture again, right here. All right. So what is our surface that's furthest in the x direction? So now we're looking at it this way. What's the surface that's furthest in the x direction? X equals 2. Very good. So it's the plane x equals 2. That's the thing that's furthest in the x direction. So that will be our upper bound here. And then what's the surface furthest back in the x direction? It's just going to be -2. So those will be our first two bounds for these right here. So if we go in the x direction, we stop at this wall. We don't kind of stop at this curved edge right here. Okay, well, that means that it's going to look a bit different if we smush this. So let's smush this. We smush it in the x direction, and we have something in the YZ plane. What shape will we have if we smush this in the x direction? That's right. It's going to be a circle this time. So if we smush this in the x direction, we get rid of that dimension. Then we have y and z right here. And what's the equation of the circle? Well, you could probably guess it's going to be y squared plus z squared is 9. All right. Now, this will help us think about the 1D part a little bit better because these 1Ds were just constant earlier. So this was the 2D surface. Now let's think about the one-dimensional curve with y. So we're going in the y direction. And the thing furthest in the y direction is this curve here. And then the thing least in the y direction, or the most negative y, will be this curve right here. So right here, we're going to have negative square root of 9 minus z squared and positive root 9 minus z squared. And then finally, and then here we're going to do the same thing, only we have our upper circle with z, and then our lower circle with z. So this will be root 9 minus y squared and root 9 minus y squared. And then finally, with both dz and dy, the lowest and highest values for both of these end up being -3 to 3 right here. So that would be how we would set up our final pair of integrals here. So this way ended up being a bit different here. So we ended up having a circle as our boundary right there. And it may not just be circles in the future. We may get other things like, oh, maybe we'll get like, I don't know, like a parabola like this, or maybe we'll get a diamond shape or something else. So we can have any manner of these two-dimensional projections here. So anyways, that was a really good exercise. We saw all 6 different ways of doing this. Now you might ask, okay, well, which one of the 6 should I have done? And that depends entirely on what function we have. So it really depends on the function, whether you want to integrate with respect to x, y, or z first. That really depends there. So which order depends on the function. So kind of like how we saw with double integrals, sometimes we get an undoable integral right here. So we need to flip the order. All right. So we're effectively creating slices of cubes of, oh, I missed that. Okay. All right. Yeah, I don't know. I wouldn't focus so much on the hypervolume part. That's probably one of the more rare applications of this. I would focus more on it being some kind of density. So like maybe you have like a probability distribution with 3 variables. If you want to find the probability of something happening with 3 variables, you would end up doing a triple integral. So it's kind of like a 3-dimensional version of your bell curve. All right. So as everyone predicted earlier, we can use triple integrals to find volumes here. So if we just do the triple integral of 1 right here, that will give us our volume because we're adding together all of these tiny little cubes, these tiny little dv's, and that's going to give us our total volume once we add up all of them. Okay, so what we're going to do is we're going to describe the solid region whose volume is this. And notice that there's no function here, so we can imagine it as a 1, and rewrite the triple integral in the order dy, dx, dz. So this is more practice rewriting all of those integrals here. All right, so let's see here. In the way they originally wrote it, they have dz first, right? So remember, these are 2D shapes, these are 1D shapes, and these are just points or numbers. All right, so my first surface is z equals 4. So z equals 4 is just a plane. Okay, so we have a plane like that. This, oh, not curved. There we go, that's a little better. All right, so z equals 4 will be our upper bound for z right here. And then our lower bound will be this, x squared plus y squared over 4 is equal to z. So this is another paraboloid, although it's going to be a very kind of wide paraboloid because we're dividing by 4. So we have our paraboloid kind of coming up here, like that. So we have this paraboloid, it's kind of making a cup underneath our plane right here, or a bowl, excuse me. Okay, so then let's crush down the z dimension and see what's going on in the x, y plane right here. Our upper bound for y is root 16 minus x squared, which that's going to be a half circle right here. And then our lowest curve for y will be 0. Okay, so this is what it looks like when we have 2 curves. And then finally with x, we go from 0 to 4. So we're actually going to ignore that. And we're just going to focus on this part since x is only going from 0 to 4. This means that we're only doing this in the first octave here because we have x and y being positive here. So this is going to be this plane on top, a quarter of a bowl underneath, and then this is all going to be in the first octave right here. All right, so now we need to rewrite this in a different order. So we need to do this in the order dy, dx, dz. Okay, so let's write down our bounding information. So we have z is 4. We have z is x squared plus y squared over 4. That's the bowl. And then we have x is 0 and y is 0. So we're in the first octave here. So we're bound between all of these. Now let's rewrite this and let's do it in the order that I want. So we have the integral of 1 dy dx dz here. All right, this is where we're really going to put our skills to the test here with changing the order. So let's think about surfaces in the y dimension here, right? So what's our least amount of y? What's the surface that's back here, bounding us with y? Yeah, y equals 0. That's right. So we have y equals 0 is kind of like a wall back here. And then what's the surface right here? What's the furthest positive with y? It'd be this paraboloid, right? This is as far in the y direction as we can go in terms of a surface. So what we need to do is we need to solve this for y. So we have 4z is x squared plus y squared. Y squared is 4z minus x squared. And then y will be the square root of 4z minus x squared here. And we take the positive square root because we're in the first octave. So that is going to be our upper surface here. All right, so to recap, we had our y equals 0 kind of plane back here, and then we had y equals the hyperplane right here. All right. Then we do this in the x direction. So we're going to smush everything with y, right? So let's smush everything with y. What do we have? Well, now we're in the xz plane, and we have what I'm shading in right now. So we have something that looks like a flat line on top and then a parabola underneath. Okay, now we're doing this with respect to x. So let's see here. What is our lower bound with respect to x? What's this line right here? This is x equals 0, right? And remember, we're doing 1D curves right now. So the back curve is this x equals 0. Even though it's a little bit silly to call a line a curve, this is technically, mathematically a curve. Now, the furthest to the positive direction in respect to x we can go is this parabola, right? So what's this parabola going to be? Well, we're in the plane y equals 0, right? Because we're in the xz plane where y is 0. So we have 0 is root 4z minus x squared. And we could solve this. 4z is x squared, or x is 2 root z right here. All right, so we have 2 root z right here, and that's going to be this x as a function of z. Then finally, once we have that bound, we're going to crush the x direction, and all we have now is the z-axis here. So what's our lowest point on the z-axis that we have? Well, it's going to be 0. And then what's our highest point on the z-axis? It's going to end up being 4. So there we go. We were able to reverse the order of integration right here. And to be honest, that was mostly an exercise in changing the order of integration. Actually doing this integral would not have been too hard in the order that it was written in. Well, actually, wait a minute. I don't want to speak too soon. No, scratch that. We would have had to use trig sub for that. Never mind. I wouldn't have wanted to do it in that order. All right. I'm not sure this order is any better. Is this order any better? Nope, not much better. So this was just a practice in changing the order. Okay, let's do one more problem here. Well, do we have time? All right, hopefully we have enough time. Find the volume of the cap with height 1 of the sphere x squared plus y squared plus z squared is 4. Now, what do they mean by a cap? Well, let's draw our sphere. So we have a circle going this way in the xz plane. We have a circle going this way in the yz plane. And then we have a circle going like this in the xz plane. That's probably the worst sphere I've ever drawn, or anyone's ever drawn. So this is our sphere right here. This is of radius 2 right here. And then the cap, what is the cap? It's where we kind of slice off the top. So we slice off the top a distance 1 down from the top. And we kind of have this like little dome right here, but it's not quite a hemisphere because it's still angling to the side here. So we're trying to figure out the volume of this kind of top cap here if we were to slice off the bottom of the sphere. Okay, so let's try to find the volume of this. Well, if we use a triple integral for that, it's going to be the triple integral of 1 dv. And then the region is the cap. Okay, well, let's actually write that as a real integral here. I'm going to do z first. I kind of just do that by default. And I guess I'll do y and then x. All right, let's go ahead and do this. So what's our lower bound for z? Well, our lower bound for z is where we kind of cut this off, right? So this is going to be what? It's going to be 1. That's right. So remember, this is radius 2, right? So if we go down 1, we're at a height of z equals 1. And then what would the top part be? So the top part's going to be the top of the sphere. And the equation of the sphere with respect to z is the square root of 4 minus x squared minus y squared. Okay. And then I'm actually going to worry about this in a moment. So I'm just going to do the integral with respect to z and then worry about going over the area here afterwards. So I do this. I have the integral of 1 with respect to z is z. And I have this going from 1 to 4 minus x squared minus y squared. All right, and then if I plug this in here, I have root 4 minus x squared minus y squared minus 1. Okay, now we're crushing everything in the z dimension, right? So we're crushing this cap down. So we kind of squish this cap, and we end up having this circle as our result here. So if we kind of squish the cap down, we're going to have the circle here. So what's the equation of this circle? Well, if we squish this down, we're at z equals 1, right? We squish this to be z equals 1. So let's plug that into here. Oh, thank you. Sorry, did you see this? So I'm going to squish down the cap, and we squish it down to be this circle that I've kind of boldly drawn here. So this circle lies on the plane z equals 1. So I'm going to substitute that into here to get my circle. So I have x squared plus y squared is 3. So this is going to be in the xy plane. It's going to be a circle of radius 3. Okay, now I actually have to do the integral this time. And I don't know about putting a bunch of square roots of things in my integral. So I think rather than integrating this with respect to x and y, what would you guys suggest that I do here if I'm integrating over a circle? We'll use polar coordinates, that's right. So rather than viewing this as x squared plus y squared equals 3 in terms of rectangular, I'm going to change this remaining double integral into polar coordinates. So the polar coordinates are like the cavalry here, and they're going to save us from doing a nasty integral. So if I change this to be polar coordinates, I have 4 minus x squared minus y squared. That's 4 minus r squared. And don't forget, if we have polar coordinates, we need that extra r. So we have r dr d theta. All right, if we're going over a circle of radius 3, our r could be as low as 0 right here. And our highest will be where we go out to the circle of root 3. And since we're going all the way around the circle, our theta will go from 0 to 2 pi. Okay, now I'm going to do my, my multiplication thing here. Since this is only an integral with respect to r, I could just imagine that I have the integral of 1 d theta right here. And then I'm just doing the single integral of root 4 minus r squared r minus r. Like that. All right. So now I do the integral of 1 with respect to theta. I get theta, and then I just plug in 2 pi minus 0. So this is just going to be a 2 pi. Meanwhile, with this, in order to do this integral, I could do u is 4 minus r squared, and du over negative 2 is r. So that's going to be how I handle this right here. So this is going to be negative 1/2 the integral of root u du. And then this part I don't need u sub to deal with. So I'm just going to do this integral separately. So I have r squared over 2 from 0 to root 3 right here. All right. Oh, they should have given us 2 pages for this one. So we have 2 pi. This is going to be u to the 3/2, but then I divide by 3/2, which is multiplying by 2/3 here. Shouldn't the 1/2 then not be with the rightmost one because it isn't with respect to u? Yeah, the 1/2 is only attached to this. Oh, yeah, the 1/2 is only attached to this integral right here. How did I know x squared plus y squared was 3? When I squished this down, I was at z equals 1, and I plugged 1 into here, into my equation, and then that gave me x squared plus y squared is 3 here. Okay, let's finish this real quick, although this is honestly a Calc 1 integral. So we have negative 1/3 u to the 3/2. And then we have minus, what's this going to be? This is just going to be 3/2. Okay, now with this, let's see, this was 4 minus r squared. And this was going from 0 to root 3. Oh boy, this is so icky. Okay, so if we plug in root 3 here, we have 4 minus 3 is 1. So we're going to have negative 1/3 for that. Then when we plug 0 in here, we have 4 to the 3/2, which is 8. But we're subtracting that, so we're going to add 8/3. Okay, so this ends up being 2 pi, and then we have 7/3 minus 3/2. And I'm just going to leave it like that because we know how to do fractions here. All right, so that's it with triple integrals, with at least in rectangular coordinates. Now keep this last example in mind here, how we were able to use polar coordinates to our advantage. Next time when we do more triple integrals, we're going to use cylindrical and spherical coordinates to make a lot of these way easier or even possible when they otherwise would have been impossible. So I will see you guys on Wednesday. Oh, I also have a funny story to tell you about triple integrals next time. So you that to look forward to. So I'll see you guys next time.